I have to give you a warning. I'm going to give two talks, one here today, and then another actually right after this session. So I will tell you, you stay here. Don't come to my second talk because I'm part of the organizers, and somehow the organizer of this main conference put my talk to the conflicting session. I have to go. Please excuse me. So that's why I'm going to introduce probably in this short talk both topics a little bit so that you can also learn my second talk as well. So yeah. And also, it's a kind of ironic. This talk is a newer work than what I'm going to present in the session after this. So I get a little bit of mix up about the chronological order. So it's a little bit challenged. Essentially, what I've been working on is to create variations of the framework called the hash chemistry, which is kind of artificial chemistry model that tries to, demonstrate some kind of open-endedness of the artificial life system without much complexity of the model itself. Model is very, very, very crazily simple. And yet how much we can produce. And the big spoiler, this one, the Cellular hash chemistry is not so great. The second one is actually much better. So yeah, the first part is kind of my failed attempt. But anyway, probably many of you already know that the open-endedness has been very active in the AI data science machine learning communities, especially because of the Ken Stanley, Joe Lemon, and Lisa Soros. They made this blog post already 7 years ago. Time flies. And then now many AI researchers are jumping into it. Can you create the artificial intelligence system or artificial life system that keeps producing new solutions without converging to any, the best optimal solution? And the issue we are trying to address in this open-endedness context is to consider what kind of the problem space you should create. Typically in the evolutionary computation, you set up some kind of optimization function. As soon as you define the function, it's over in some sense, because evolution does not really work on any well-defined fitness landscape. So how can you create undefined fitness landscape and with infinite amount of possibility? So that is the one big issue we have been trying to address. Our approach is to use the bottom-up approach, just like the distributed Viking or distributed Ghost last year. Can you create a distributed system that creates in a bottom-up way those implicit functions? And one concept I've been advocating is instead of evaluating the things at one scale, you should allow those entities to form higher order entities. So this is a concept I published 5 years ago. It's called a cardinality leap. If you have entities at the individual level, if you consider the combinations of those entities by mathematical logic, it's always the cardinality of the possibility space is going to be jumping up from countably finite to countably infinite, or from countably infinite to uncountably infinite. So if you have this kind of, possibility for entities to form the multi-set, it's a very easy way to achieve the very, very vast search space. And then this is the work I published also 5 years ago. It's called hash chemistry. It's a very, very simple thing. So here you have a two-dimensional particle system. Different particle has different colors. It's sampled from the 1,000 possible elements. The rule is crazily simple. You just grab the local aggregation here, and then take a look at it. In this case, there are 3 particles, and then we need to come up with some methodology to evaluate how successful this 3-particle system is. And then we give up the idea. It's too difficult to design the physical space, so therefore we're going to pray for God, right? So we have the God in every general programming language called hash function. We are not supposed to question the internal mechanisms, right? And then you need to believe that's going to give you the oracle. Any kind of data structure you throw at this hash function, it's going to give you a number deterministically. And that's a perfect example of avoiding all the physical chemical details. And instead, you just believe in the hash function as a universal evaluator. And then whatever hash value you get, depending on the value itself, you're going to decide maybe this group is going to replicate or removed, etc. And it already creates a very beautiful dynamics. Oops, sorry. What happened? Okay, here. So this is the previous one, the publishing back in 2019. All the things that I was doing here in this simulation is select the local region, put into hash function, based on the hash value, you do replication or deletion. That's it, with a little bit mutation. Already you see some kind of interesting dynamical behavior, evolutionary behavior. And again, I'm still talking about the previous work. Sorry. Okay. And this already showed, interestingly, that the combination of the self-reproducing entities just kept increasing linearly. So keep in mind, this is the log scale in terms of time. The different types that successfully replicated just keep increasing over time in the linearly. So this is the cardinality leap we were able to demonstrate in the hash chemistry. And they also did a little bit of unbounded growth in terms of the average number of entities, particles that they're replicating together. So this is the plot showing that the average number of particles involved in the self-replication event. Statistically, this is considered to be unbounded, although the maximal number of particles tend to be bounded. So there's a little bit of mixed results previously. And these are the unresolved problems from the previous work of hash chemistry. First, computation is very expensive. The density can get very, very high, and then you need to simulate a very large number of particles. That was the primary motivation why I was working on the variations. Second is that unboundedness is something that we want to address. We want to have, boundedness was something we want to address. I want to have the variation hash chemistry that keeps demonstrating unbounded growth of complexity. And then I did two things. One is cellular version, which I'm going to talk about now. And another one is non-spatial one. Spoiler alert, the second one was better. So you're going to give the suboptimal example, sorry. Okay, so this is the model variant I'm going to talk about after this session. Again, please do not come to my session. Stay here, okay, as organizer. Yeah, I have the full paper published in the proceedings of CEC this year. So if you are interested in this non-spatial version, please take a look at that. Okay, so this non-spatial version, that I said, it's actually showed very interesting unbounded growth, but still, it's boring because there are no interaction, because the system is non-spatial. You actually lost all the interesting, the ecological interaction between evolving entities and the context dependence. For example, your success should depend on who is nearby. That kind of interesting spatial local interaction is completely lost in the non-spatial version. That's what I wanted to address in this cellular version. Okay. Now I'm moving into my part, and I already spent 8 minutes. So this looks like a cellular automata, but it's actually not. So this is yet another version of the artificial chemistry. I'm going to minimize this. Yeah. So you have the spatial grid. Each grid point may contain one of the 1,000 possible elements. And everything is going to be pretty much similar to what we did for the original hash chemistry. Grab the local configuration, evaluate success, and put it back, depending on how they performed. So here's a detail, but I'm going to just explain by word. So a little bit the tricky part is that you need to choose different sized regions because you want to represent competition between smaller entities and the larger entities. It was not so trivial how you can do it. In this particular implementation, we selected 4 randomly selected regions, non-overlapping regions. In this case, you have 2 big regions, 2 small regions. All of them were put into the hash functions. And it's a 4-way competition. Whatever has the highest hash value after normalization, you choose that as a winner. And the winner is going to create the offspring. It's a little copy of itself pasted into one of those regions of the same size. Is that clear? So that the competition actually overrides the another pattern of the same size that did not really have as high hash value. And you repeat this. And it's rather difficult to define what is a time in this case. We consider that the sum total of the overwritten areas, if that area accumulated updated areas became the same as the total area of the space, then we consider that might be the one good time step because everybody had at least one chance to get updated. And you repeat this many times, and then this happens. Okay, I love spatial model. Again, this is not a cellular automata, pretty much the same as the particle-based hash chemistry, but you see some rewriting events happening, right? And what's nice about this compared to the original particle model, it's very, very fast. The algorithm is so easy, there's actually no neighborhood detection. Yeah, so that actually skips most of the computational process, and then you see some global changes also happening. Even though we didn't really put anything fundamental into this, you see sometimes you see more reddish squares arising, sometimes it's going to be bluish, sometimes greenish. So they are all spontaneous. So you see some long-term evolutionary dynamics of different kinds of particles spontaneously coming up. And I don't have any full explanation why and how this is happening. It just happens. Okay. Any question about this? Is it clear? Yeah. So each time step contains multiple rewriting events so that the sum total of the rewrite area is going to be equivalent to the size of space. So this is what we get. For example, if you plot the time series data for the number of particles of the one particular type for all the 10,000 particle types, this is what happens. So clearly you see the transition from one dominant type to another. So evolution keeps changing the population makeups. So this is very interesting. It's definitely not just pure randomness. And also, obviously, by definition, almost, the system is showing the cardinality leap because the area to be evaluated can be just 1 pixel, can be 2 by 2, can be 10 by 10, can be 50 by 50. There are a large number of possible sizes. So therefore, if you look at the second plot, this is a number of different types that successfully replicated. This is almost tautological because we are doing this. The number of possible types that successfully self-replicated increased over time, linearly over time. Okay. And this is one nonsense plot I had to generate. If you compare the computational time, the original model took about this many minutes. This is non-spatial version I'm going to talk about in the session after this. This is cellular version, very, very fast. Again, this is nonsense because those are 3 completely different systems. It's not really comparing the apple to apples. It's apple to oranges. And yet, when I was writing full paper for CEC community, reviewers requested this plot. So sorry, if you are the reviewer, I apologize, but they never understood what I was doing. This is a completely different system, but I just generated, okay, 2,000 steps, this, and this. Yeah, we did it. So both of them, non-spatial version and cellular version was actually much faster than original particle-based one because we don't really have to do the neighborhood detection. And cellular one is actually much, much faster, even compared to the non-spatial version, which is good at the cost. That's why I said it's boring. The hash chemistry converted to this cellular grid, it did not really show much of the adaptation to begin with. So these are the plots showing the actual fitness value after some rescaling. The higher, the better. After the initial couple of generations, it stays pretty much the same. Yeah. And this is maximum value. This is the average value. Average value even showed a little bit of a decrease. So these are kind of the underwhelming results. So even though long-term population dynamics are going on, it's kind of questionable whether or not this is indeed showing some biological evolution in traditional sense. And also, this is very depressing results. I did a similar approach. How many cells are actively replicating together? And this is the maximal number of entities that successfully replicated over time. This is the average number, the same analysis as what we did before. And then conducting statistical analysis, both of them show the bounded growth. It's kind of depressing. So here's the overall summary. And by looking at this chart, you don't have to come to my second talk. Okay. So this is the original hash chemistry published 5 years ago. These two are proposed in this year, the non-spatial version, next one, and the cellular hash chemistry. In simple words, the cellular version captured pretty much the same feelings and tastes as the original one. So in that sense, we were successful in capturing the original taste, but there's a huge issue in terms of adaptive behavior, and then growth was bounded. It's kind of depressing. Compared to that, non-spatial version I'm going to talk about next session is it doesn't really show any interesting interaction between entities, but it actually did show increase of the fitness, and their growth is actually unbounded. So there is a trade-off between those. If you introduce space, we may lose these. And if you want to promote evolution in a traditional sense, you may need to remove the space to make the computational process manageable. Anyway, to conclude, we propose a cellular version, which captures the essence of the original hash chemistry, which is extremely fast. So maybe if this is so fast, maybe the typical mantra that just keep increasing the system size, and then something magical may happen, like ChatGPT, right? Put trillions of parameters, maybe some magic may happen. But right now, we are not seeing any meaningful fitness improvement, and we may need to work on something here to make both the spatial interaction and meaningful evolution adaptation. So yeah, that's what I said here. Okay, with that, I'm going to conclude. Thank you very much. I'd be happy to take any questions.